Hello, everyone. We are delighted to have you on board for today's session on strategic imperatives for the next generation data center infrastructure. I'm Rana, a technology and innovation consultant with over a decade of experience working with Stellarix. Before we dive into the topic, here's a quick overview of who we are. Stellarix is an innovation and strategy consulting firm that helps organizations achieve future readiness and sustainable growth. By combining industry expertise, technologies, and tailored strategies, we work as trusted partners from concept to commercialization to create value and meaningful impact for our clients. We span across 8 verticals, including industrials and high techs, and cover newest domains such as IoT, data centers, AI, sustainability, and others. We provide strategic support to our partners from pre-conceptualization to monetization by offering different services, including horizon scanning, ideation, scoutings, and others. Now coming back to our topic. Overall, the last couple of years, AI has moved from pilots and proof of concept into everyday's product used by millions of people. What's changed is not just adoption, it's the scale. The biggest challenge for organization is no longer access to model, talents, or even capital. It's whether the physical infrastructure needed to run AI can actually be built fast enough. At Stellarix, we work with enterprises, hyperscalers, and colos on AI strategies and digital infrastructure transformation. So what we'll share today is grounded in what we are seeing across real deployments. To understand why infrastructure has moved to center stage, we need to look at where data center expansion is breaking today. I'll invite my colleague Deepak, who leads our industrials and high-tech verticals and work closely with clients on architecture and delivery side. So Deepak, please share your insights on the global AI infrastructure landscape.
Thank you, Rana. Thank you for inviting me for this meaningful webinar. And you rightly pointed out about the infrastructure strategy, because what we have been observing is that traditional approaches are not doing great in this fast-paced environment now. So we are in the middle of the industrialization of AI. For nearly 2 decades, data centers were majorly functioning as an air-conditioned warehouses, you can say, for the servers. But now they are rapidly transforming into high-density AI factories, and it is very much visible through this chart on the left side as well, where we can see that the power demand coming from data center is increasing exponentially. In 2024 itself, we could see that there were approximately 400 terawatt hours of power demand that came from data center, and which is anticipated to grow at a 15 to 20%, 22% of CAGR in the range of 1000 to 1400 terawatt hour by 2030. And this is a very huge gap that we are anticipating, a big range where we are seeing that power demand might grow into the coming future. But the problem here is that the grid supply that is coming is still growing at a very consistent rate, which is 2 to 4%, which is creating an execution gap here. Now, for any organization, the execution gap is the primary risk to their market share. And we are already seeing the consequences of this execution gap. The consequences are like extended timelines for grid connections, longer lead times for critical components such as transformers or other high voltage equipments, and growing uncertainty around time to power for their data center initiatives. So, if any companies or their competitors secure the on site power generation capacity, while the another organization is stuck between the time to power gap, the execution gap that we are saying, that definitely they are going to lag into the AI race. So our analysis suggests that the data center investments are going to rise around 6.5 to 7 trillion dollar by end of this decade. And around 60% of it is going to be for the technology developers only. Now we have slowly started seeing a shift where now the investment is increasing in the cooling and electrical infrastructure as well. So this is giving a big opportunity to a lot of different kind of organizations which are operating into the cooling system, thermal management systems, and giving another organization who are working around the power distribution units to optimize and be a part of this larger ecosystem. So it is directly going to affect the speed to market, capacity, and competitiveness of organization. So let's move further and see how this power and thermal barriers are going to act and how they are also accelerating along with how the demand is increasing. So just before this decade, what we could sees that the rack densities were generally hovering into the range of 10 to 30 kilowatt. But now the stability is changing. Earlier, stability was there into that power capacity, and that helped in shaping the entire data center infrastructure, which was revolving around the power distribution, cabling, floor loading, cooling design, and everything. But now, when we see the generative AI coming into play by the year 2022, things have started changing, and now we are seeing that AI clusters are pushing well beyond 100 kilowatts as well. This was the transition era where we could see rack densities started growing exponentially and moving towards the 300, 500, 600 kilowatt. And even by the end of this decade, we have estimates that it might reach even up to 1 megawatt per rack. So put this into perspective, let's take an example where we know that NVIDIA is working around the GB200 GPUs, which are already integrating Blackwell GPUs and Grace CPUs, and able to provide powers roughly around 120 kilowatt per rack density. And they have already started working on the next round of the model GB300, which can provide 135 to 140 kilowatt per rack density. So at this point, the challenge is no longer how much power you have at the site. Now challenge has shifted to the power distribution, whether if you get all the power to your data center, whether you can distribute that to the rack efficiently or not. So this is where the earlier 415 volt AC system, which are currently used for the data center, are also failing to some extent, because the more we increase the capacity of per rack, we need high amperage, and with high amperage, more and more copper demand increases, and we have to increase the thickness of the copper cables. And again, that goes for a lot of power losses, conversion losses, a lot of capex improvement, and everything. So now there is innovation going around developing the 800 volt DC architecture as well. So this is where the power distribution is going to tackle that power delivery wall issue for the data center of high capacity. So high voltage DC is going to reduce the copper mass eventually. It is going to help with fewer conversion steps to improve usable power at the rack, and the economics will improve further as the rack density is going to increase. Here, where the execution gap is becoming very real. So if you attempt to power these densities, eventually you will have to shift towards a new architecture, and which is the organization are trying to do. So beyond a certain density threshold, power delivery architecture is shifting from a design preference to a physical constraint. Now let's look beyond the density threshold. What are the other physical limitations of these data centers as we move towards the very high density architectures? So another challenge that comes into play is the thermal management, the thermal wall that we can call it. So now the shift is happening where we are moving towards the liquid first architecture. But let's first understand what is this physical wall or physics wall that is happening, which is pushing the innovation into the cooling system. So earlier it was air dominated era, we could say, where different air related technologies or air cooling technologies were being used into the data center, and it was effective when we were between the 30 to 40 kilowatt of the power range, and the lot of optimization was being done into the airflow channels and everything. But now, with the increased density, we have moved towards this transition zone where now we are working in the hybrid environment of cooling plus air. So now, with that transition, slowly companies have started moving towards the efficiency zone where now they are majorly trying to rely on the liquid first architectures, where direct to chip cooling is one of the technology they are relying. They are working on the single phase or two phase immersion technology, where the entire racks are being immersed into the dielectric fluids for the cooling purpose. And then in the future, what we are anticipating is that there will be a total convergence of IT and infrastructure, where microfluidic cooling is going to take place. But again, for that, companies like Nvidia and companies who provide the cooling technologies have to work hand in hand to build those kind of systems. There are a lot of examples that are coming here. For example, JetCool has patented their microconvective direct-to-chip cooling technologies where they are trying to improve the cooling solutions. Companies like CoolNet or Inspurs are coming up with immersion cooling technologies, which they are claiming that can support up to 150 kilowatt per cabinet of power up break densities to say. A lot of other solutions are also coming around, Munters, SLCS, and a lot of many companies, even the startups, are coming up with a lot of waterless and water-based cooling technologies to support these high density power racks. But again, there is one another critical element for any data center planner to consider is at what stage the liquid cooling is being introduced. So here you can see on the bottom left part into this table that if liquid cooling is considered at the design phase into the early design part itself, then cost per megawatt comes somewhere around 400,000 to 600,000 euro per megawatt. And it has a significant impact. It can reduce the 40% of physical footprint. But again, if you have already done the design and it is being done at the late integration, it is certainly going to increase the cost per megawatt, which is going to extend to 2 to 2.5x of the early design stage. But again, it is going to give you significant output impact where you will be able to increase the IT capacity by at least 2x. So eventually, going towards the liquid cooling is going to have some kind of positive impact onto the overall data center architecture. So once organizations accept that liquid first is inevitable, the real question becomes is where, how, and with whom organizations should participate or partner for this transition to happen. So this is how we are seeing the scenario as of now.
Yes, Deepak, I complement your findings in the last few slides, be it about the execution gap being the primary risk to an organization's market share, or the physical constraint while scaling beyond a certain rack density threshold, or the liquid first cooling being inevitable in the coming future. Now we can also discuss what approach industry leaders are taking to solve the infrastructure problems.
Sure, Rana. So most organizations are approaching AI infrastructure as one time build versus buy decision. But in practice, what we are saying is a bit different scenario. So here you can see that it totally depends on what kind of workload you are planning to use into the data center. That totally translates into your infrastructure strategy. So if an organization is planning to train a lot of AI models. So if they are going into the training part, then definitely they should approach towards a build strategy. They should build their greenfield data center facilities by themselves because they are eventually going to give them a long time of dollar per AI compute capacity eventually, and for the long term they will have flexibility to scale them as they want it to be. But when an organization is only trying to have the AI inference into their data center and they are not putting the load of training the AI, then going with the co-location partners might be a suitable strategy because it is going to provide you shortest time to capacity. Eventually, the faster time to market will be there for when you go with the colos or any kind of partnership. And the trade-off that you are going to do is with the control because you will be in the partnership game there. And if the organization's purpose is only for the fine tuning or the experimental AI applications, then going for the retrofitting of the legacy system also might do the work here because it works best at less than 180 kilowatt of capacity per rack capacity. But again, there is a high risk of stranded upgrades when you are going for the retrofit solution. But again, what we are observing is that that becomes a suitable approach when you do not have a lot of model training load or AI inference load onto your data centers. If you fail to choose the right path and you go towards the wrong path, then there are certain risks that organization has to think about. For example, if you overbuild for short-lived workloads, let's say your objective was the fine tuning only and you optimize your data center for model training as well, then definitely it is going to have a great impact on the capex. So you'll have to decide what is the right objective then only you should decide that what should be the right approach and what kind of infrastructure strategy we should adopt. There are certain examples coming from companies like AWS, companies like Google, who are doing the partnership into the developing countries to build these kind of specific purpose built AI hubs into these emerging markets. For example, Google has already committed $15 billion of AI data center campus in India, which is built with local partners in collaboration with Adani majorly. Similarly, Meta has also done alliance with the Reliance to purpose build these kind of AI hubs in uh, Indian market. So you see that these are completely purpose built where they are looking what is the end purpose and accordingly they are deciding their strategy whether to partner or whether to build their own facility. Again, when the systems are being designed, there are certain pattern that we are observing what the organizations are thinking during the designing phase. So once leaders accept that reality, the question shifts from whether to change to how to architect the AI at scale. So what we are seeing in practice is that organizations are converging on a small number of architectural patterns, not a lot of different technologies. So first pattern is coming as liquid first architecture. This does not mean adding liquid cooling to an existing design. It means that designing the facility around liquid as the primary thermal backbone and using air only where it still makes sense or where it is completely necessary. So this distinction matters because beyond around 80 to 100 kilowatt per rack, air cooling stops being a scaling mechanism and start becoming a liability for organization. So liquid eventually becomes the inevitable solution for you. Then the second is power to chip efficiency by using HVDC or some kind of modular power infrastructure. So this is another winning pattern here. So most AI facilities do not fail because they lack the grid power like we discussed earlier. The challenge is whether the power that is being received at data center is properly being supplied to the rack itself. So at high densities, every additional conversion step eventually add energy wastage, the conversion losses. So that's where leading operators are trying to simplify the power path by moving towards the high voltage DC and modular power infrastructure. And the third one is heat aware architecture. So even when waste heat is not monetized today, leading facilities are designed so that heat can be extracted, routed, and reused in the future. In parts of Europe, we have observed, particularly in Nordics, we have observed that data centers are already integrated into district heating networks, and a lot of such kind of projects are already coming into picture. You can see the example for all these three patterns where we know that Microsoft has already built purpose-built AI data centers with liquid, completely liquid cooling infrastructure, and they are building the closed-loop liquid cooling racks. So at facility level to handle the GPU heat efficiency. NVIDIA on the other side using the pattern to by building 800 volt HVDC power architecture for their next generation AI data centers. And similarly, there is a host shift data center which is partnering for water cooling and inbuilt waste heat recovery systems. So all these patterns are being utilized by organization based on their different infrastructure strategy or different end objective of the data center. Now, the waste heat recovery has been one of the most, I would say, interesting topic in the AI infrastructure because most discussion assume that waste heat is automatically valuable, but in reality, most waste heat has negative value. It usually costs money to move, store, or use that waste heat. So the economic reality of heat recovery depends on two major things that you can see right side onto this chart. It's about the heat quality and proximity of your heat sinks. So the closer your heat sink is and the better the heat quality, then it becomes a profitable use of that waste heat for you. So this is the quadrant where high quality and strong sink eventually turns into the real monetization, which is being used by some organization into Nordics where they are using the district heating network because everything is within the proximity itself for there. But if you look from the legacy data center perspective, usually the output heat quality was coming from the air cooling solution, which was at a very low grade, somewhere between 30 to 40 degrees Celsius. And even the heat sinks were not into the proximity. So that another created a barrier how to reuse that waste heat. But now the things are changing a lot across the globe. A lot of regulations are coming into the play. We are seeing a lot of different implementation examples happening across the globe. So even Germany's parliament has passed an energy efficient act where the waste heat reuse is now a mandatory requirement for any new data center facility that is being built into that specific area. From the implementation example perspective, Microsoft is running a project in Finland with Fortum, where they are deploying one of the world's largest data center heat recovery projects, where they are using waste heat from new facilities to supply 40% of district heating for a lot of people which are into the nearby surrounding area. They plan to do it by end of 2026. A lot of projects are run by Equinix and other organizations as well into this specific space. So ultimately, what we can say here is that if regulations, energy prices, or local demand shifts, then heat reuse is going to be possible really without putting too much pressure on building the infrastructure.
Yes, Deepak. Regulations and policies do play an important role here. Multiple EU countries are mandating reuse of waste heat from data centers. For example, Norway requires data centers of greater than 2 megawatt capacity to assess heat reuse potential, while Germany mandates new data centers to reuse 10 to 20% of waste heat. However, the full recovery needs further incentives from the governments. So, we are nearing the end of our conversation. I would like you to recommend some key strategies to organizations working in this space.
Sure, Rana. So the key decision for data centers is whether to build, whether to buy, or whether to partner. We already discussed about it, but again, eventually, if you observe the entire market, this is becoming as a very key decision for any management executive to understand how should we approach the new data center, considering that it is a fast-paced environment and technology is developing at a very faster level. New workloads are coming into play. So what we are doing is why this decision making is harder than before. We first need to understand that because now the demand curve of AI is very much uncertain. Workloads are scaling faster than ever. Then there are asymmetric constraints, the constraints related to power, cooling, even land acquisition, grid timelines are moving at a different speed. Like the execution gap that we have seen earlier, that gap is something which is widening, which is creating another challenge for the data center strategy. Then the technology inflection. Now GPU densities and thermal profiles are changing faster than the facility life cycles. So again, unless we match those different life cycles or somehow come up with a plan to reduce that execution gap, then only we can move forward with slightly better speed in executing and building those high capacity data center. So the potential market approaches can be, for example, like hyperscalers. They can opt for sequencing the build, buy, and partner decisions across different time horizons. For example, if you are an AI native company, then using a co-location early while designing for the long-term capacity might be a suitable approach. And if the organization is a co-location operator, then partnering with utility and cooling innovators can be a suitable approach to stay density relevant because density is going to increase continuously. There is no stopping that considering the vast use of AI that we are seeing right now. So finally, we are coming down to the final strategic imperatives for the next generation of data centers. So far, we have talked about power density, cooling limits, HVDC, liquid architecture, and waste heat. But the real story is not about any single technology. It is about how infrastructure decisions are being made differently by organizations that are pulling ahead. So what we are seeing is a clear shift here. The leaders are no longer asking what is the most efficient design. Instead, they are asking what design keeps our AI roadmap viable under uncertainty, under different load, under different requirement. So what we can say is that power is no longer just a utility problem. Cooling it doesn't becomes cooling is no longer an efficiency lever only, and infrastructure is no longer a backend function only. It has become a game of capacity, speed, and strategic optionality decision. So there are some irreversible decision that has to be made by organization carefully, and reversible decision has to be made very fast. And importantly, They are not doing everything themselves as of now. They are choosing where to build, where to buy, and where to partner. So, based on time to capacity, if there is one takeaway from this webinar, then this is what the takeaway is. The next generation of data center is not going to be defined by peak efficiency matrices. Instead, it is going to be defined by how quickly they can adapt without redesigning. So this is going to be the suggestion from my side about this entire webinar and the takeaway from this and the strategic choices that an organization needs to make when they are planning for any specific data center or any future plans for next 5 years.
Thank you, Deepak, for sharing these valuable insights. And thank you, everyone, for joining us today. If you'd like to explore an AI data center readiness assessment, power and cooling strategy, or next generation infrastructure roadmap with Stellarix Consultancy, type Stellarix in the chat and our team will follow up. Thanks once again, everyone, for your time and your participation.